Okay, so this will be a quick video about the rules of oxidation number. There are 6 rules that we need to know when we consider an oxidation number. And just to remind ourselves about what an oxidation number is, let me give you a quick definition. So the oxidation number is a purely formal concept which regards all compounds as ionic, and it assigns charges to the components accordingly. Another thing is that it provides a guide to how the electrons have been distributed and the relative charges on each individual atom that form in a compound, whether it be covalent or ionic. And then it also helps us understand the redox procedure in general, as in which part of the element or the compound is being oxidized and which part of the compound is being reduced. So the first rule we have is ionic. The rule involved in this is that we need to treat the compound as totally ionic, in the sense that if the compound is ionic, then the charges on the ions are the oxidation number. For example, if we have the Cu2+ ion, obviously this is an ion because its charge is different to what it usually would be, of 0, and oxidation number is equivalent to the ionic number, or the ionic charge. Next is electronegativity. Electronegativity, we'll find it written on in the periodic table. It basically demonstrates an atom's tendency to attract electrons. So as we know, halogens, so group 7, would be the ones that want the electron the most, because they only need one electron to fill its outer shell, whereas group 1 alkali metals would have the least tendency to gain an electron, because in fact they're trying to lose an electron, because they only have one electron in its outer shell. So the most electronegative, which is for your information, which is fluorine, is the molecule where it's assigned a negative charge, in the sense that fluorine is always a negative ion, and it will always get an oxidation number of -1. Whichever is most electronegative will receive the negative charge, as the electrons are more likely or will be going to that particular element. Next is the sum. Okay, so the entire rule is assign oxidation numbers or charges accordingly to give the overall charge on the molecule or ion. That is, the sum of the oxidation numbers, taking into account signs and coefficients, is equal to the overall charge on the molecule / ion. So I think that's fairly self-explanatory. Then the next one is from an elemental perspective. The oxidation number of atoms in an element is always 0. So for example, H2. Even though we have 2 hydrogen molecules, or 2 hydrogen atoms, the overall charge is 0. Whereas if we have O, the charge is still 0, since it's just the sole element. However, if we have H2O, whilst the overall charge is 0, that's due to the balancing of these electrons. -2 here, and +2 here, +1, and -2 from the oxygen. And then groups 1 to 3. The elements in groups 1 to 3 always have the group number as their oxidation number, in the sense that if you're an alkali metal, like let's say potassium, your oxidation number will always be +1. Whereas if you're an alkali earth metal like beryllium, your oxidation number will always be +2. And so on and so on. And lastly, the maximum oxidation number. This is a key concept that we need to learn, and that is the maximum possible oxidation number for an element is its group number, in the sense that potassium cannot have a group number, an oxidation number of +2. That is not possible, since it cannot lose 2 electrons. Otherwise, because if it's already lost 1 electron, it becomes a noble gas, and noble gases, of course, cannot lose any more electrons, since they're extremely inert and